All right, here's the deal. I have a couple confessions to make. One, when I set off to make this video, I had hoped to keep it to around 15 minutes, but I've had a little too much fun with this project, and as a result, I failed at that. So I've instead decided to make it a two-part series, parts 1 and 2 on Igneous Rocks. The second confession I have, I'm actually going to introduce at the beginning of the next video because it's way more pertinent then, and if I talk about it now, you'll probably forget by then, and then it's useless. So yeah, look forward to that at the beginning of part 2. I often talk about how a foundational understanding of geology engenders a deeper appreciation for the places we visit, the places we inhabit, and the places we call home. For me, thinking in terms of geologic time inspires humility, wonder, and awe for this world around me. But there's a downside to thinking in terms of geologic time too. Thinking geologically allows me to think beyond the bounds of human history, which, as empowering as it can be equally ignorant and can disrespect the very foundation on which my ability to appreciate this land is built. As an American of European descent, especially one whose life revolves around understanding the land around me, it's imperative for me not to take for granted the horrific history that provides that privilege. In the following video, I'll take you to a handful of places around the country to look at igneous rocks in the field. Places that, prior to European colonization, were inhabited by the Ho-Chunk, Eastern Shoshone, Molalla, and Kalapuya people, as well as likely others. Both of our stops in Wisconsin are on Ho-Chunk land. In an 1832 treaty with the American government, the Ho-Chunk were forced to cede this land. Decades of ethnic cleansing followed as both federal and state governments repeatedly, though unsuccessfully, sought to remove the Ho-Chunk from Wisconsin. Our stop in Wyoming is on Eastern Shoshone land. The Eastern Shoshone were forcibly removed from their native lands with the Fort Bridger Treaty of 1868, which established the Wind River Reservation that still exists today. The treaty was the second in 5 years with the Eastern Shoshone, and the resulting reservation covered a tenth of the land they previously occupied. Our final stop in the Willamette Valley of Oregon is on land previously occupied by the Molalla and Kalapuya people, estimated to have numbered around 15,000 prior to the arrival of European settlers. Settlers first arrived in 1812, bringing with them diseases previously unknown to the Molalla and Kalapuya. By the time of the Willamette Valley Treaty of 1854, which forcibly removed both groups from the valley altogether, an estimated 600 people remained alive. These histories are brief and certainly fail to do justice to the atrocities these people suffered. But it's important to honor and to own this history, and to recognize that Indigenous people are not relics of the past. They remain in this land and continue to persevere amidst a backdrop of ongoing colonialism and oppression. And just as I hope that the geologic understanding of a place inspires appreciation and action on its behalf, I also hope that a glimpse into the cultural history of a place can inspire the same. Okay. Take 3.7. Igneous Rocks. Here we go. So, before we dig into things, let's put things into a bit of context. You may recall that igneous rocks are one of 3 primary rock types that make up the rock cycle. The other 2 are sedimentary rocks, which I actually made a video about. You should check it out. And the other is metamorphic rocks, which I'm currently working on a video for. But no matter the rock type, all rocks are made up of minerals. All rocks are made up of minerals. All rocks are made up of minerals. Remember that. You can actually learn that in another video I made about minerals, though that video is a little rough around the edges because it was the first in this project and it was a bit of a trial. But that aside, I want to preface this video by saying that there's simply no way I can cover all of the amazing things about igneous rocks in the course of a single video. So I'll be focusing on just basic igneous rock identification, and will generally avoid broader scope topics like volcanology, etc. But maybe, if I can get funding, that would be a fun future video. That's enough of non-geology. All right, so what exactly are igneous rocks. And while this definitely does not pass as a highly technical definition, I like thinking about igneous rocks as any rock that was formerly molten, i.e. just really friggin' hot. Molten rock actually goes by two names, depending on where it exists. If we see it at the surface of the Earth, which is obviously the only place we ever see molten rock, we call it lava. That's not a surprise to you, but that stuff has to come from somewhere, right? And that somewhere is deep below the surface of the Earth. And when it's down there, we call it magma. So magma exists in chambers deep below the surface of the Earth. And when it decides it wants to fly the coop, it erupts through a volcano and becomes lava as it does so. So you might be thinking, why would we call molten rock two different things depending on where it is? Well, it turns out it's actually really important because igneous rocks can form from either lava or magma. Actually, in some crazy cases, both. Naturally, geologists have to complicate things with fancy words. So we like to say that igneous rocks that originate as magma, beneath the surface of the Earth, are intrusive. Whereas if that magma decides it wants to be lava, we call it extrusive. And recognizing an igneous rock as either intrusive or extrusive is one of two primary means of identifying igneous rocks that geologists use. The second is recognizing the relative proportion of silicate minerals in a given igneous rock, but we'll get to that in a second. Don't panic just yet. And yes, obviously, you should go watch the minerals video because it'll help, blah, 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 blah. I'm not gonna belabor that point. So, you're probably wondering just how in the heck you're supposed to tell if an igneous rock is intrusive or extrusive, let alone how much of that rock is made up of silicate minerals. And I would not blame you for thinking that's an absurd expectation. But luckily for us, igneous rocks actually make it pretty easy to do. Remember in sedimentary rocks when we talked about composition and texture? Well, composition and texture are also what we look at to identify igneous rocks. Well, in igneous rocks, when we talk about texture, we're talking about crystal size. We don't even really care about shape. We're just interested in the size of the crystals we see in the rock. Are they big and easily discernible, or are they really tiny and too small to see even with the naked eye? We care because crystal size actually tells us whether an igneous rock is intrusive or extrusive. Specifically, intrusive igneous rocks have really large crystals relative to extrusive igneous rocks, which have small or even indiscernible crystals. I like thinking about it this way. If I were a magma, where would I be most comfortable? The answer to that is in the mantle. If I'm this big, hot, molten mass, I'm going to be comfortable where everything else is also really hot and molten, the mantle. If I move out of the mantle up into the crust, then it's going to be a little colder than it was in the mantle, and I'll slowly start cooling down. If I stay there long enough, I will eventually, over a really long period of time, cool into an intrusive igneous rock. But if I move even further up, if I leave the subsurface entirely and become lava via a volcano, then it's going to be really cold relative to where I'm comfortable, right? And I'm going to cool really quickly. And it's actually crystal size that tells the story of this cooling process. And as ever, I think it'd probably be really helpful to see what I'm talking about. So, I need a wardrobe adjustment. That should do it. That should do the trick.
Perfect. This is exactly what I had in mind. For example, when a magma chamber deep under the surface of the Earth cools super slowly over lots and lots of time, all the little ions in that magma chamber have time to find their friends and form these enormous mineral crystals, like these quartz and feldspar grains in here. So see how you can differentiate and discern these mineral crystals really easily just with the naked eye? That means that this cooled super slowly over a lot of time. So granite, and this is granite, is a perfect example of an intrusive igneous rock. So this granite is actually, I'm here in this Wind River range of central Wyoming, and this stuff is over 2 billion years old. It's just mind-blowing how old that is. It's so cool. So this formed over 2 billion years ago, deep under the surface of the Earth, and then hundreds of millions of years later, in fact, between 40 and 60 million years ago, some weird tectonics lifted these rocks up into what we now know as the Wind River range. And so this is an intrusive igneous feature, and we call this a batholith, this huge igneous feature here. We call it a batholith because it's over 100 square kilometers in size. And so geologists, of course, have some weird names for different intrusive igneous features depending on some different characteristics. And I think I want to talk about a couple of those, but let's do that back in the classroom.
Yep. Great. In addition to batholiths, you should also know about dikes, stocks, and sills. There are others, but these are some of the more common ones. So dikes are simply smaller scale intrusions that cut across existing bedding planes. And actually sills are very similar to dikes, but rather than cut across existing bedding planes, they follow along them. And stocks are simply small scale batholiths, that is, irregularly shaped bodies of intrusive rock. Finally, if you don't actually know the size or shape of an intrusive feature, you can use the term pluton, which is a good catch-all for all of them. For example, we can call the Wind River Range in Wyoming a pluton, but if we want to be more specific, we can call it a batholith because we know its size and its shape. So that's intrusive rocks, but what does it look like if lava erupts and cools extrusively? If this happens, cooling occurs so quickly that all the little ions that make up the minerals don't have time to differentiate into larger mineral crystals, so the minerals end up really small, often not even discernible at all. So I actually like thinking about magma chambers as enormous parties and the ions that make up those minerals as the party goers. Stick with me here. So if you and a bunch of friends are at a party and the party just sort of fizzles slowly over time, y'all will probably leave together as a big group of friends, right? If, however, y'all are at your totally responsible party and your grouchy old neighbor calls the cops on you, well, then you'll probably split as fast as you can and won't have time to find your friends. Let's go take a look.
So that's actually what happened to all this basalt here that surrounds me at Silver Falls State Park in Oregon. About 15 or so million years ago, enormous lava flows covered massive stretches of what is now the Pacific Northwest. And looking behind me, you can actually see that this waterfall has exposed 3 of those those lava flows in the rocks behind me. You can see the individual layers there. But because lava, by definition, happens at the surface of the Earth, we know that it cools relatively quickly compared to magma in the subsurface, right? So if we look closely at the rock, we can see that it's actually kind of boring looking. There's no discernible mineral crystals in here. And while at first glance it's kind of boring, that tells us a lot, right? Because we don't see mineral crystals in this rock, we know that it cooled really quickly and is thus an extrusive igneous rock. But we don't actually have to travel halfway across the country to see cool extrusive igneous rocks. Perfect. For example, this 2 billion year old rhyolite is just outside of Baraboo, Wisconsin. And just like the basalt that we saw in Oregon, this is an extrusive igneous rock. And we know that because we can't see any of the minerals in it with our naked eye. So that just shows that we can use texture, i.e. whether or not an igneous rock has fine-grained minerals or coarse-grained minerals, to tell whether that rock is intrusive, like that granite that we saw in Wyoming, or extrusive, like this rhyolite, or like the basalt that we saw in Oregon. And the crazy thing about this rhyolite is that compositionally, i.e. chemically, it's actually really similar to the granite that we saw back in Wyoming. And so what that means is the only thing that differentiates these rocks is that one is intrusive, the granite, and one is extrusive, this rhyolite. And we can tell the difference because this rhyolite has really fine-grained texture and the granite has really coarse-grained texture. So we can use texture to identify intrusive versus extrusive, which is awesome. But that leads me to the next thing that geologists use to identify igneous rocks, which is composition. But to discuss composition, I think we should pop back to the classroom.